So firstly, hi to everyone. So initially I was saying hi to yeah, I'll now quickly do that again actually. And again, Twitch is only showing 4 people in the room as far as the number of viewers. Hi Electrical Skateboard, hi Jutlander 8, hi Michael T. Mayer, hi Puka 420. And then there's some others. Hi Peter, hi Guido. And if I've missed anybody else, I apologize. But basically, I was discussing how I was walking through how my plan initially was to talk about cosmic rays today. However, this morning, for some good reason, yeah, sorry about that, Guido. Guido, that was my first mistake of the day. I hope I don't have any more. But initially thought I was going to talk about cosmic rays, decided against it, and was like, you know what? I'm going to do carbon dating. And so I was looking around online, and I found some information about carbon dating, about how the way in which it works is that scientists or just people in general look at the ratio of carbon 14 to carbon 12. And so initially what came to mind was like, how is carbon 14 created? I mean, carbon 12 is a naturally occurring isotope of carbon. But I was curious as to how do you get the radioactive version, carbon 14? And so, can anyone here guess how carbon 14 is created? I swear to you, I did not know this until today. All right, let me get rid of the system preferences. Well, I'll go ahead and just tell you. Apparently, carbon 15 bits of carbon. Oh, that's actually a pretty good one actually. Um well, 14. Hey Adam. I'm happy you don't feel, yeah, you shouldn't feel bad because it's on me right now. I really did not know my Bluetooth was on. I'm up here just talking and everything, and you guys can't hear what I'm saying. But basically, I'm gonna go ahead and type in, and this is what I typed in earlier. How is carbon 14 made? And this is exactly what popped up. And I was actually just so happy when I saw this. So apparently, carbon 14 is made by cosmic rays. Well, not specifically by the cosmic ray itself, but it's a product of the interaction between a cosmic ray and one of the atoms in our atmosphere, producing a high moving neutron, and then this neutron ends up colliding into one of the many nitrogen 14 atoms in our atmosphere. In fact, if I'm not mistaken, nitrogen is the most abundant substance in our atmosphere. And so the nitrogen 14 ends up getting you can look at the diagram here actually. So I'll try to like make the diagram bigger. There we go. And so the neutron's created, right? The neutron ends up interacting with our nitrogen 14 atom, which nitrogen 14 is stable. 7 protons, 7 neutrons, if I'm not mistaken. One of the protons gets kicked. And whenever you have an atom lose a proton, you automatically have a change in species. So you go from nitrogen 14, proton gets kicked, but if I'm not mistaken, if the proton is kicked, the neutron basically ejected the proton, but it's now retained. And now you're left with carbon 14. And so when I found this out, I was like, "Hey, there's the cosmic ray connection." But but then I was like, "How do I turn this into a problem?" So the problem I end up, given that I wanted to initially talk about carbon dating, the problem that I end up coming up with is, and this is my own personal made up problem with a little bit of help from my physics book. I was looking around at some stuff in there, but basically, I want to be able to see how radioactive activity relates to half-life of a radioactive substance. All right, and hopefully everything I've said so far was not only one heard, but everyone's clear so far on what I'm talking about. So yeah, Guido, I did not know, and I feel bad because I'm supposed to be the cosmic ray expert. I did. That's one of the many things I didn't know. If you ask me about how showers and stuff are created and the different particles that are being produced within showers, at least the most important ones, we can have a good discussion on it. But I had no idea. This is how carbon 14 is created. And so the interesting thing about this though is that it's a naturally occurring isotope in our atmosphere. And given that it's a naturally occurring isotope in our atmosphere, we breathe and we eat it. So it's inside of us. So the idea here is that the same proportion of carbon 14 and carbon 12 that's in our atmosphere is the same proportion that's within our bodies. And that's a key thing that I want you guys to remember as we work through today's problem. All right. So let's go ahead and pull up some equations for radioactivity. So let's see, what do we get? Radioactivity. Did I misspell something? Yes, I did. Equation. I'm wondering if Wiki typically has like stuff that's very useful. See what Wiki can give us. Okay, this is useful information, but I want something that just has all the equations, just like the major equations that we want. All right. I think we will go with this one. We're just going to go with this one. See if I can get a bigger image of it. Here we go. Yeah, we'll just use this. We'll use this page for today's problem. So the very first thing I want to be able to do is, well, we're going to first start off by figuring out exactly, because I mean, you can use carbon dating to be able to, get the age of a particular thing, right? Given that you have some sample of that thing, you can figure out what the ratio of carbon 14 to carbon 12 atoms are within it. So what we're going to first start off by doing is figuring out how many carbon 14 isotopes are there within the human body. And so we're going to assume that the average human body is like, I don't know, let's go with 200 pounds, right? So let me go ahead and let me look at the comments. We don't want carbon 14 unless it's in a thick lead box. Well, luckily, because carbon 14 is actually within our body, and it does undergo beta decay. So the carbon 14 will beta decay, if I'm not mistaken, back to the nitrogen 14. And beta decay is basically going to be when you have a neutron, and what do you end up getting? I think you get an electron, a proton, and I think a neutrino. I think I would have to look at the equation and think about the rules of But I think that's it, because you're going to be neutrally charged. You get an electron, a proton, and I believe a neutrino, because the lepton number has to be the same. So you get an antineutrino actually. But yeah, so the proton stays, electron gets ejected, right? You have this high energy electron. It could be high energy electron, and you're right. So you wouldn't want too much of this in your body, right? Because you wouldn't want a bunch of electrons zipping out of your body, depositing all that energy within you. But yeah, it's a really small amount. We'll end up seeing that in a minute. So let's see. Where was I? Sorry. We wanted to calculate how many carbon 14 isotopes there are in a human body, assuming that the average human body is 200 pounds. All right, so let's go ahead and switch over to our tech sheet. It's now 12:17. I've been talking for way too long, so I need to hurry up. All right, so no indent. How many carbon 14 isotopes in the in a 200 pound person? All right, so let's go ahead and begin working out the math for this. And I'll have to correct that in just a second. There we go. All right. So to figure out that number, and I'm just going to denote this as some n initial. And of course, we're assuming the person's alive. So how many carbon-14 isotopes in a 200-pound person that is still alive? That is still... All right. So n sub 0 or n naught, another way of naming that. To get this quantity, we need to take into consideration that we have a 200-pound person, right? But the pound is a unit of force. It's not a unit of mass. And we need a unit of mass, actually. We can't start off with force. So we're going to actually have to convert 200 pounds to units of mass. And the unit of mass I like to work with most commonly for me is going to be kilograms. So we need to first figure out what 200 pounds correlates into or how it converts to units of kilograms. I was looking online because I was actually curious of this myself. And so we're going to do this together really quickly. So we're going to have to switch scenes again, guys. Let me look at the comments really quick to make sure that there's no questions. All right, so I know I can just go online and I can, you know what, for the purposes of time, we'll do this. We'll just do that. But if you want to make the conversion, you'd use the fact that the pound is related to, as far as units are concerned, breaks down to units of slags. Actually, I think you guys can see exactly what I'm looking at anyway, so let's just quickly do it. So maybe SI unit for pound. Units for pound. Let's look at this. But I saw something before, and I think it was like it's equal to a slag times, where a slag is going to be the unit of mass times some sort of acceleration. I can't remember what the unit is, but it's not a hard conversion to do. But let's just go ahead and just say pound to kilogram. And so we're starting off with the fact we have a 200-pound person. Remember, that's a unit of weight or force. And we're converting this into a unit of mass. In this case, 200 pounds is equivalent to 90 kilograms here on Earth. 200 pounds on a different, planet would be different in kilograms. All right, so we get 90.7. I'll do 90.72. All right, so I'm just going to go ahead and erase the 200 pounds within the tech document. And round this to 90.72. And this is going to be kilograms. All right. And so now that we know the average mass, or we know the mass of this particular person, we need to be able to figure out how much of that mass is in the form of carbon. Carbon-14 in particular, or just carbon in general. So, for the next part of our calculation, we need to, so let's go back to the internet. The internet's going to be definitely our friend for today. Let's figure out how much carbon in the human body. This will work. This will work for us. And so this basically gives us a breakdown of the composition of the human body. And it states here that by mass, there's 18.5% carbon in the human body. So we need to multiply. So let's go back to our tech document. We need to multiply this by a factor of 18.5%, which is going to be 0.185. And I probably should make sure I'm keeping track of the units. Yeah, 0.185. So this is going to be the amount of mass that's actually carbon. And the very last thing we're going to want to do, now that we've set up the math for how much carbon is within the human body, we need to figure out how much of that carbon is actually carbon-14. Now remember that our body is composed of different types of carbon. You have your carbon-12 in there, and you have your carbon-14. So we need to figure out exactly how much carbon-14 is in the atmosphere, because apparently there's that much carbon within our bodies. So, or at least the ratio is the same. So let's go back to the internet. And how much carbon-14 is in the atmosphere? I think this is... this actually gives us the physical value. But I think what this is actually saying is that there is 1 atom of carbon-14 per 10 to the 12 atoms of normal carbon. So of that mass, so I think I'm understanding this right. So of that mass, let's see what everyone else is, if anyone else has stated anything. Okay, no? All right. So of that mass, let's go ahead and switch back to our tech document. Of that mass, we're basically going to state that of the amount of mass, carbon mass within our body, we're going to state that every one carbon-14 atom out of wait a second, no, this isn't what I want to do. Not yet, at least. I need to figure out how many. I need to figure out how many carbon-12 atoms there are in our body first. So we know it by mass, and what we can now do is we could take the I think it's the atomic weight of carbon, and the atomic weight of carbon I think is 12. I think it's 12 grams. So we'll use that actually. So to figure out exactly how much hmm. Right. For every one carbon atom, okay, I see. Sorry, guys. Again, my brain went blank there. For every one carbon atom, there's 12 grams of weight. So we need to convert grams to kilograms. So what we're going to end up doing now is we're going to put 0. That's grams. So 0.012, and this is going to be kilograms. I really do feel like I probably should have put variables for this first and then start plugging in numbers, because I'm trying to keep track of what each of these numbers is representing, and that's kind of difficult right now. So bad math right now. But I think this is good. We're taking consideration that we've converted 200 pounds to 90.72 kilograms, and of that total mass, 0.185 or 18.5% of that is in the form of carbon. And so that gives us the total mass of carbon for the human body, or for the 200-pound person. And now we're converting that mass of carbon to number of carbon. So far, so good. But now we need to convert again from, and this is carbon-12 though. So now we need to convert, and of course this is also assuming that most of the carbon is in the form of carbon-12, which is right. But now we need to convert the carbon-12 to carbon-14 to get an actual number for carbon-14 isotopes. And so earlier I saw that it should be roughly for every carbon atom, or carbon-14 isotope or atom, there is on the order of 10 to the 12 carbon-12 atoms. And I believe this is the correct math that we want to go with. So I'm going to go ahead and typeset this. I'm missing something here. Oh, I put it in the wrong place. It's like, what's going on? All right, let's move this to the right place. It should work here, though. Oh, come on, guys. Oh, I didn't copy everything over. That's why. Okay. All right, so this is where we're at so far. And so I'm noticing now that, yeah, I really should try to keep track of these units. But basically, this should be the number of carbon atoms, number of carbon-14 isotopes in the human body. And so when you do the math for this, we end up getting that number equals, and so I'm going to quickly do the math. Thanks, Adam. So yeah, guys, make sure you're checking me what I'm doing here, because I as you can tell, I can make mistakes. 90.72 times 0.185 times, or divided by 0. Why do I get the feeling that this isn't going to come out right? But let's see. So Right. So 90.72 times 0.185. I want to divide this by, I'm doing this all on my computer, guys. 0.185. I want to divide this quantity by the product of 0.012 . You know what? Now I realize something. What I'm doing wrong here. So I didn't actually put this right. That first ratio, the 1/0.012 kilograms, I need to use Avogadro's number. For every 12 grams of carbon, there's 6 times 10 to the 22 atoms of it. So that's what I'm forgetting here. Kept looking at it and I was like, this looks weird. So I'm gonna quickly look up what Avogadro's number is. So Avogadro's number is it's roughly 6 times 10 to the 23. So let's go to tech. 6 times 10 to the 23rd power. And this should correct the calculation. And that's the number of atoms that we get for every 12 kilograms or 12 grams of carbon. All right, so this should come out right. So I need to add a factor of 6e23. All right. So far so good, and this is going to be times in the denominator 1e12. All right, and I get a number of roughly 8.4 times 1, 2, 3, 4. 4 times 3 is 12, 12, 14. So 8.4 times 10 to the 14. And I'm rounding here, guys. So 8.4 times 10 to the 14 power. Hopefully this calculation is correct. But we get roughly 8.4 times 10 to the 14 carbon 14 isotopes in a 200-pound person. All right, so we have an initial number to start with. So far, so good. So now I want to be able to look at and see exactly how does the activity of carbon 14 change over some period of time, or at the very least starting off with this number of carbon 14 isotopes after its first experience of activity. Exactly what value would we end up getting? All right, so I want to calculate the initial activity is what I'm getting at here. So no indent. And the activity, I gotta explain what that is actually. The activity is basically the number of, in this case, the number of decays per unit time. And so to continue with this part of our problem, I'm going to go ahead and we're going to go back. Let me make sure I'm not missing any of the comments here. Oh, no need to apologize, Peter. Hey, Susie. So at the current moment, just to catch everyone up who's new here, we are now trying to calculate what the initial activity for the radioactive substance carbon-14 is, because carbon-14 is a radioactive substance. Let's see. So to calculate the initial activity, what we're going to do now is we're going to go to back to our browser, and we're going to go back to that list of equations we were looking at. Here we go. And so, as we can see here, I'm going to zoom in a little bit. The symbol A for these set of equations here represents the activity of the sample, where we can basically use the initial activity A sub 0 or A naught is equal to lambda times n sub 0 or n naught. And we've calculated n naught or n sub 0. So that's our initial amount of substance that we're beginning with. In our case, we calculated it to be like on the order of 10 to the 14 carbon-14 isotopes. And we want to get A sub 0. But to do that, we need to know what lambda is. And lambda in this equation represents the decay constant, the decay constant. Yes. We are not going to try to calculate the decay constant for carbon-14. We're just going to look it up. So let's go ahead and let's pull up another browser tab, and we're going to put in decay constant for carbon-14. And there you go. In units of per seconds, it's roughly 4 times 10 to the negative 12, but I would go ahead and use a value of 3.9. So our initial activity, let's see, going back, so I need to switch us back to our tech document. Our initial activity, A sub 0 or A naught, is equal to, and given that we've already just seen the equation, I'll just go ahead and plug in the values. The product up between our decay constant, which was 3.9, times, I think it was 10 to the negative 12. Let me go back and make sure. Yep, negative 12 seconds. And I'll try my best to keep up with the units here. And this is going to be multiplied times the value that we end up getting for n naught, or n sub 0. 8.4 times 10 to the 14. And so what we end up getting is that this value ends up coming out to equal, I really wish it was that the 3.9 just evenly divided it, or evenly like multiplied out with, the 8.4. The 4 would do better actually. But yeah, I'll just go ahead and use my calculator. Not evenly divided, but like 3.9 times 8.4. That gives us 32.76. That should be a negative 12. And so we should end up getting 3.2, and I'll just round that to 3.28 times, so 10 to the negative 12 and a 10 to the negative 14 would give us a 10 squared, and we have to give another factor of 10 given me converting to scientific notation, so 10 cubed. So 10 cubed is what we end up getting, and this should be this is basically going to be the number of decays per unit time. All right, so that's our initial activity. And so now what I want to know is if our initial activity is somewhere around what I'm seeing here to be somewhere a little bit above 3,000 decays per second, I wonder how long does it take for the number of decays to dwindle down to just simply being 1 decay per second. And so we can actually go back to that. I actually might be able to finish this in the amount of time, but by like 1 o'clock. So I'm going to go ahead and copy and paste this and just simply modify it. So how much time must elapse for the decay rate, not the decay constant, but the rate of decay, or the activity actually, for the activity to become 1 decay per second. Let me go back to the comments to make sure I'm not missing anyone's comments here. Now the reason why I'm sorry, I'm missing out. I missed some of the conversation here. So Larry states, and hi Larry, welcome to today's stream. I know the answer. There is exactly 1 isotope of carbon-14, not counting nuclear metastability. So can we do a calculation for someone that died 2,000 years ago? So you know the amount of time. So what would you want to calculate with that? You want to calculate how much carbon is like within their body still? Or no, you want to know like, I think I understand what you're saying. So if we were to go back, let me see what you guys can see right now. So this is what you're able to see. Let's go ahead and go back to the internet and look at the set of equations for radioactivity. Not that, here. So we could determine the activity based off the equations I'm seeing here. We could determine the activity, what the activity would be today for a person that died 2,000 years ago, if that's what you wanted to do. But my whole plan was to initially see what happens, how much time must elapse for the activity to drop down to 1 decay per second, and then compare that to how many half-lives it would take for the amount of the substance to get down to just being 1 carbon-14 isotope left. But we can do this though. We can definitely calculate with what would be the activity after 2,000 years. So yeah, okay, we can quickly do that actually. So let me go ahead and switch scenes and go back to what we have here. So we have the initial activity. We have the initial activity. And so all we need to do now to calculate the final activity after 2,000 years is just take this very last. So wait, you guys cannot see what I'm looking at here. So let me first switch the scene. All right. So what we can do is we can take the very last equation that we see there, where we have A is equal to A sub 0 times e raised to the negative lambda t. Where in this case, we already know what lambda is. It's the decay constant that we just used a few minutes ago. And t in this case will be 2,000 years. which we need to convert to units of seconds. So let's go ahead and quickly do that. And if I'm not mistaken, I mean, the activity should still be, it definitely won't drop down to 1. It should still be, I want to say fairly, it will be much, much greater than 1, that's what I'll say. It's because the half-life of carbon 14 is like 5,000 some odd years. And 2,000 years isn't that bad. Or isn't that much compared to 5,000. It's close, but it's not. Let's go ahead and make the calculation, though. So going back to our tech document. So how much time, or let's change this to what is the activity after? What is the activity after 2,000 years? All right. So I'll go ahead and just copy and paste. That makes it faster. And so what we end up getting here is that A sub 0, or A, is going to be equal to must be equal to the value of A we've already calculated, which is 3.28 times 10 to the third power number of decays per second. And I'll put this in parentheses. And we're multiplying this times E raised to our two values. We have the decay constant being one of them, which is this, I can actually just simply copy and paste this. 3.9 times 10 to the negative 12 seconds decays per second. And we need to multiply this times the elapsed time of 2,000 years. But we need to convert 2,000 years to units of seconds. And so I'll do this actually. This will make it go faster. For every, I'm gonna use a quick little conversion factor I remembered. For every pi times 10 to the 7 seconds, you get 1 year. And I hope this comes out looking right. If it doesn't, I'll have to make the correction. And yes, I think that's right. I think that's right. Okay. And so, and lastly, I'm going to convert the 2000 to scientific notation. 2.0 times 10 cubed. All right. So the activity value should end up coming out to be, did I forget something else? I feel like I forgot something. This is a decay. So I think I forgot a negative sign. I think I forgot a negative sign there. Let me increase this so you guys can see what I'm doing here. But just to verify, yeah, it should be a negative sign there. All right. That's now correct. And I'm going to go ahead and plug this into my calculator and see what I end up getting. And I think we'll end it here, but I do want to talk a little bit more about radioactivity. So E raised to the, let's hope I can get this all right. So 2 times pi times 10 raised to the third power is that right? Right, because I need to also incorporate the fact that I have that 10 to the negative 12 and at 3.9. And it's all negative. There we go. So negative 2 times pi times 10 raised to the third power times 3.9. This might not be a fun one. Only reason why I'm saying that is because I don't think my calculator is having a good. It's showing 0, even though that makes sense. But I don't know if it can calculate the number of decimal places. Let's see. Out to that number of decimals. So 2 times. So negative 2 times 3.9 times pi. All right. Times, and let me go ahead and throw this 10 raised to the negative 12 power. How is it doing that? Okay, so I'm getting 1. So far, let's see. Got 3.92 since the times 10 cubed. Let's see. Interesting, actually. Times, what am I missing? Pi. Times 10 to the 7th power. All right. I finally got the, the answer I was trying to get before. So 0.78. 0.78. And that's what the exponential comes out to equaling. So it looks like, I mean, just looking at this, if we could think of 7/8 as being close to, like, I mean, 0.78 as being close to 0.75, it looks like the activity, it decreases by 3/4. So 0.78, and that makes sense. The activity should decrease, right? The rate of decays per unit time should begin to slow down over time because you're losing more and more substance. But let me quickly calculate what it comes up to be exactly. So 3.8 or 3.28, excuse me, times 10 cubed. And so now we get an answer of roughly 2.56. 2.56 times 10 raised to the cube power. Per second. So this is the number of decays per second. I apologize for that, for taking so long there. So C14 has a very long half-life. So when I was looking at it online, it said the half-life was like roughly like 5,000 something. Hey, Coleslaw. That reminds me of Coleslaw. Well, welcome to today's stream. Oh, as of right now, we were looking at the activity. But earlier we calculated the number of it is coleslaw plus sloth. But I apologize. So let me explain exactly what's going on here. Well, welcome to today's stream. And so the objective, well, my initial objective was to be able to make a comparison. Like weeks, cool. That's weird because I'm. There we go. Yeah, keeper of maps. I think that's closer. I think it's like 5,300 years or so is the half life of carbon 14. But let me explain what I was attempting to do initially, though. Okay, is that the more exact? I think that's the more exact value. But initially, what I wanted to do was be able to compare how the amount of elapsed time that it would take to get to an activity of 1 decay per second compares to the amount of time for all the carbon 14 isotopes to decay to such an amount such that we only have one carbon 14 atom left. Well, no. I don't want anyone to feel bad or anything. Because honestly, when I first started off doing this stuff, I did not understand it. I think my first experience with chemistry was back in high school doing stoichiometry, if that's how it's pronounced, and basically that was me balancing chemical equations. Wait, there's only one isotope of carbon? Yes. Maybe I've been saying it the wrong way. What I mean is that you're right. There's only one isotope of carbon 14, but what I'm calculating is the number of carbon 14 atoms, and that's what this initial calculation was. Given a 200-pound person that's still alive, how many carbon 14 atoms are in his body or his or her body? I apologize if I made that confusing. But Larry, you're absolutely right though. There's only one. Yes, the N not corresponds to number of carbon 14 atoms. I am so sorry for that. Yeah, so what we ended up doing is we took 200 pounds, converted that weight to units of mass to get 90.72 kilograms for a 200-pound person, and then we multiplied that by 0.15 or 185 to take into consideration that only 18.5% of the mass is actually in the form of carbon. And then I just assumed in that instance that mostly all of that mass is carbon 12, which is the reason why I'm using. So yeah, one of these streams I'm gonna do some more coding, and we can code everything up. But yeah, I apologize, Larry. And for anyone else I may have confused with my my wording for things, I apologize. That was not my intent. But yeah. So I think to answer Adam's question, so after 2,000 years, if you start off with this amount, so 8.4 times 10 to the 14 carbon 14 atoms within a human body, and then that person unfortunately died. Not unfortunately, but ends up dying. I don't want to say unfortunately, but if the person ends up dying, then after 2,000 years, or not even a person, any living thing that ends up dying with that number of carbon 14 isotopes initially, will end up having an activity after 2,000 years of 2.56 times 10 to the third power decays per second. Yep, carbon 12 and carbon 13 are the ones that. So yeah, carbon 12 and carbon 13 are the ones that are stable. Yep. If you know, if you'd want to, I mean, that's cool with me. Um. So. Oh wait, you're talking about CosmoQuest. I'm assuming you're talking about CosmoQuest. So this is what I'm gonna do. I don't mind. But yeah, Kosloff, I'm thinking. Are you thinking about volunteer work for CosmoQuest or for the streams that I'm doing? And don't worry. I mean, most of the stuff that I'll be talking about, it won't be related to chemistry. Thank you, Guido, for clearing that up. Um, Actually, this is a very interesting thought. So let me send you my email, and I don't mind putting it on here. So I'm gonna post my email here, and so hopefully I don't start getting a bunch of crazy like messages to my email. But I'm gonna post my email, and I'm not too sure about. Well, we can definitely just talk more about this offline. All right, guys. The time is now 1:05 p.m. and I hope that I did not confuse anyone more than what I'm feeling like I may have confused you guys today. Um, Hopefully you guys got something out of this though. But fun calculation to do. And I guess until I see you next week sometime. Not at all. I'm gonna choose something that's it's. But no, yeah, I'm gonna choose something that's really really good though. One of these days. Thanks, guys. Thanks, Jutlander. Thank you, Susie, for putting that information out for me. Um, all right, guys. I'm gonna go ahead and sign off now. And you know what? This time, actually, I think I'm gonna go to the Weekly Space Hangout Cruise Slack and see if I can like generate some good ideas for my next stream. You guys are always having a lot of good discussions on there, so I'm gonna see if I can like choose one of the discussions and like make up a problem for it. All right, guys. Well, until next week, I'll be back on Wednesday at 12 o'clock p.m. Central Time. All right. Bye, guys. That's right. I have a bunch of different PDFs I need to upload. I'll do that. Thanks, Keeper of Maps. All right. Bye.